For as long as we have looked up, the moon has shown us a familiar face. Well, it is a constant in our night sky, a disk of craters and seas that has inspired myths and poetry for millennia. But there is a profound mystery bound to our celestial neighbor. We only ever see one side of it. This cosmic synchronicity means that the other half, the far side, remains perpetually hidden from our direct view on Earth. For ages, it was simply a blank space in our imagination, a realm of pure speculation. People called it the dark side. Though this is a misnomer, it receives just as much sunlight as the side we see. Its true nature is not darkness, but concealment, a grand cosmic secret waiting to be unveiled. The questions that arose from this hidden hemisphere were as vast as the space that separates us. What landscapes existed there? What geological stories were etched into its surface, different from the familiar patterns of the near side? This wasn't merely a matter of curiosity. Understanding the far side was crucial to completing our understanding of the moon as a whole, and by extension, the history of our own planet and the solar system. The reason we only see one lunar hemisphere is a beautiful piece of celestial mechanics known as tidal locking. Over billions of years, the Earth's gravitational pull has slowed the moon's rotation until it reached a perfect equilibrium. Today, the moon rotates on its axis in almost the exact same amount of time it takes to orbit our planet. This gravitational dance keeps the same face perpetually turned toward us, like a loyal partner. The far side, therefore, always faces the cold, empty void of deep space. For most of human history, its existence was a logical deduction, but its appearance was a complete mystery. It was a blank canvas onto which we could project our greatest hopes and fears about the unknown. Our first glimpse of this hidden world came in 1959, when the Soviet Union's Luna 3 probe swung around the moon and transmitted grainy, indistinct images back to Earth. The pictures were rudimentary, yet they were revolutionary. They confirmed what some scientists had theorized. The far side was not just a mirror image of the near side, it was a different world. The images revealed a surface almost entirely covered in craters, a pockmarked landscape that spoke of a violent, ancient past. The large, dark, smooth plains of basaltic lava, characteristic of the near side's man in the moon, were conspicuously absent on the far side. These missions confirmed the far side's crust is significantly thicker and geologically older than the near side. This barrier to our vision has made the far side a place of scientific desire. Without direct line of sight, communication with any probe or lander becomes an immense challenge, a puzzle that for decades seemed too complex to solve practically. So, while we sent robots and humans to the near side, the far side remained untouched. The first fleeting glimpses we got were from spacecraft flying past, revealing a terrain that was starkly different, more rugged, more ancient, more heavily cratered. It lacked the vast, smooth plains of cooled lava, the so-called maria or seas, that dominate the near side. This difference hinted at a fundamentally separate evolutionary path. Why was it so different? What forces shaped this alien geography? The answers, scientists believed, were not just on the surface but deep within the moon itself. To truly understand it, we had to do more than just fly by and take pictures. We had to land. We had to touch the soil to analyze the rocks and to listen for the faint geological whispers of its formation billions of years ago. A mission to the far side was not just another step in space exploration, it was a leap into the unknown. It was a challenge that called for new ideas and bold engineering, a test of our ability to overcome fundamental obstacles. And it was a challenge that China decided to take on, opening a new chapter in our exploration of the cosmos. To unravel the secrets of the hidden hemisphere, China embarked on one of the most ambitious lunar missions ever conceived, the Chang'e program, named after the Chinese goddess of the moon. The culmination of this effort was Chang'e 4, a mission with a goal that had never been attempted before, the first ever soft landing on the far side of the moon. This was not a simple task. The mission presented a monumental communications challenge. Since the far side never faces Earth, any lander there would be completely cut off. It would be unable to send or receive signals, like talking to someone on the other side of a mountain with no way to get a message over the top. China's solution was both elegant and technologically demanding. Before launching the lander, they sent a dedicated communications satellite, Queqiao, Magpie Bridge. The name references a Chinese folktale where magpies form a bridge across the Milky Way. Queqiao was placed in a halo orbit at the Earth-Moon Lagrange Point 2. From that vantage, it could see both the far side of the Moon and the Earth. It acted as a constant relay station, catching signals from the lander and forwarding them to mission control. With communication solved, the stage was set. On January 3, 2019, Chang'e 4 descended toward the von Karman crater, a vast basin inside the even larger South Pole Aitken Basin. This site was chosen for its immense scientific interest. South Pole Aitken is one of the largest, oldest impact craters in the solar system. Scientists think the impact may have punched through the Moon's crust, scattering deeper mantle material across the surface. The landing sequence was a marvel of autonomous engineering. Because of signal delay, the lander performed critical descent phases on its own. The successful landing was a historic moment, precision and planning rewarded. Once the Chang'e 4 lander was safely on the ground, it deployed its companion, a six-wheeled rover named Yutu-2, or Jade Rabbit 2. This intrepid explorer rolled down a ramp and onto the lunar soil, becoming the first vehicle to ever traverse the far side of the Moon. The rover rolled away from the lander, heading into the von Karman crater, a strange, ancient landscape. Yutu-2 was equipped with a suite of scientific instruments, a panoramic camera, a ground-penetrating radar, a spectrometer. As Yutu-2 began its slow, careful journey, it sent back breathtaking images. The landscape was a pale, dusty gray littered with small craters and rocks. Sunlight, unfiltered by atmosphere, cast sharp, dark shadows. The ground-penetrating radar was put to immediate use, peering deep beneath the surface. It revealed a top layer of loose regolith, then layers of ejected rock and buried craters below. These findings pointed to repeated impacts over billions of years. The rover's main objective was to search for signatures of the Moon's mantle. The lunar environment is brutally hot by day, brutally cold by night. To survive the 2-week lunar night, the rover enters sleep mode, relying on a radioisotope heater unit. At sunrise, it wakes and continues exploring. To this day, January 29, 2026, Yutu-2 still roves the far side, having traveled kilometers and far outlived its design life, continuing to send new data from this once hidden world. One of the most profound discoveries. From the Chang'e 4 mission, the rover had found material that likely originated from the Moon's mantle. The Yutu-2 rover's spectrometer analyzed the soil in several locations and detected distinct chemical signatures, olivine pyroxene. These are not typically found in large quantities in the lunar crust. Lunar crust is mostly feldspar-rich rock. The presence of these mantle-like minerals on the surface was the smoking gun scientists had been searching for. It was compelling evidence the colossal impact that created the South Pole Aitken Basin excavated material from deep inside the Moon and flung it onto the surface. This discovery is a game-changer for planetary science. Understanding the composition of a celestial body's mantle is key to understanding its formation and its thermal evolution. Before Chang'e 4, our models were based on indirect evidence, seismic data from the Apollo missions, and analysis of volcanic rocks that erupted from the interior. These methods provided an incomplete picture. Finding actual mantle material on the surface is like a geologist being handed a sample from Earth's mantle without drilling hundreds of kilometers deep. It provides a direct physical piece of the puzzle, allowing for a much more accurate understanding of the Moon's internal structure. The initial analysis suggests the lunar mantle may be different from previous models. The composition of minerals found by Yutu-2 points to a more complex and varied interior. This has sent planetary geologists back to their drawing boards, refining theories about the Moon forming from debris of a giant impact with early Earth, and how it cooled and differentiated into distinct layers: core, mantle, crust. The data from the far side is providing a crucial new calibration point, helping build a more accurate history of our nearest celestial companion. Ultimately, Learning about the moon's interior helps us understand the formation of all rocky planets, including Earth. The Earth and Moon share a common origin. The Moon's geological evolution is intertwined with Earth's history. By studying these ancient mantle rocks, we gain insight into planetary differentiation and the composition of the raw materials that formed the inner solar system worlds. The discovery on the far side is not just about the Moon. It is a whisper from the deep past about the cosmic story we are part of. It is a piece of our own origin story, found on a distant, dusty plain. Another discovery of immense significance from China's recent lunar missions: definitive detection of water molecules in the rocks and soil. While earlier missions from other nations had found evidence of water, particularly in the permanently shadowed craters at the poles, the Chang'e 5 mission, which returned samples to Earth in 2020, provided the first on-site confirmation in a mid-latitude region. Instruments on the lander detected the spectral signature of water, H2O, within the lunar regolith. The amount was minuscule, about 120 parts per million, equivalent to a few ounces of water in a ton of soil, but its presence was unmistakable. This finding transforms our view of the Moon from a completely arid desert to a world that holds a vital resource. This water is not in liquid form, sloshing around in underground pools. Instead, it is locked within the mineral structure of the soil and in tiny beads of glass. Scientists believe most of it was delivered by the solar wind. The solar wind is a constant stream of charged particles flowing from the sun, and it includes hydrogen ions. When these hydrogen ions strike the lunar surface, which is rich in oxygen-bearing minerals, they can combine to form water molecules. The Chang'e 5 analysis showed that the soil was wetter in the lunar afternoon, suggesting that this process is ongoing, with water being formed and then potentially lost as the surface heats up. This dynamic water cycle, however small, is a fascinating area of new research. The implications of finding water on the Moon, even in small quantities, are enormous for the future of human space exploration. Water is one of the most critical resources for sustaining life, for astronauts to drink, to grow plants for food, to create breathable air by splitting the water molecules into hydrogen and oxygen. Transporting the vast amounts of water needed for such a base from Earth would be prohibitively expensive. The ability to extract water directly from the lunar soil, in situ resource utilization, or ISRU, could be the key to viability. Furthermore, water is also a potential source of rocket fuel. By splitting water into its constituent elements, hydrogen and oxygen, a lunar base could function as a gas station in space. This would dramatically lower the cost of missions to more distant destinations like Mars. Launch lighter, refuel at the Moon, then push outward. It really could change everything, you know. Beyond the discovery of mantle rocks and water, China's analysis of lunar samples has also brought renewed attention to a resource with almost science fiction-like potential: helium-3. Helium-3, He3, is a light, non-radioactive isotope of helium that is extremely rare on Earth, but is thought to be much more abundant on the Moon. Like the hydrogen that forms water, helium-3 is deposited on the lunar surface by the solar wind. Over billions of years, the Moon's soil has become saturated with this isotope because it lacks a magnetic field or a thick atmosphere to deflect the incoming solar particles. Initial analysis of the samples returned by the Chang'e 5 mission confirmed the presence of helium-3, providing real-world data to support this long-held theory. The reason helium-3 generates so much excitement lies in its potential as a fuel for nuclear fusion, the process that powers the Sun, where atomic nuclei are fused to release immense energy. On Earth, fusion using hydrogen isotopes is difficult and produces some radioactive waste. Fusion with helium-3, in theory, would be much cleaner and safer. No radioactive byproducts. It represents a potential holy grail for our planet's energy needs. Of course, the path to helium-3 fusion power is long and fraught with challenges. First, we do not yet have a working fusion reactor capable of using helium-3. Second, while more abundant on the Moon than on Earth, helium-3 is still present in very low concentrations. It would require mining and processing enormous quantities of lunar soil, hundreds of millions of tons to produce a significant amount of fuel. The logistics and cost of such a large-scale industrial operation on the moon are staggering to contemplate with our current technology. Despite these hurdles, the confirmation of helium-3 in lunar soil provides a powerful long-term incentive for developing a lunar economy. It shifts the conversation about the moon from a place of pure science to a potential source of resources that could fundamentally transform our civilization. It could drive the development of the heavy-lift rockets, robotic mining equipment, and processing plants needed to make it a reality. China's discoveries have added a concrete data point to this futuristic vision, making the prospect of lunar resource utilization less a matter of speculation and more a matter of engineering and long-term commitment. Well, it's an exciting possibility. China's discoveries on the far side of the moon do more than just add new pages to our science textbooks. They fundamentally reshape our perspective on humanity's future in space. The confirmation of mantle materials, the on-site detection of water, the tangible presence of helium-3 are transforming the moon into a dynamic world of immense strategic and scientific value. It is no longer just a destination for flags and footprints. It is a repository of knowledge about our past. It is a potential storehouse of resources for our future. This new understanding opens up a universe of possibilities, from sustainable lunar bases to a new era of clean energy on Earth. These missions mark a significant shift. For decades, deep space exploration was dominated by two superpowers. Now, the success of the Chang'e program shows the cosmos is opening up to new nations. This multipolar reality can drive innovation, and it creates a compelling need for international collaboration.